Hello, good evening,
sir.
friends. Good evening, friends. Very good evening to all. After a long gap, we have started this academic program by starting this class and Zoom meeting. And I think you are all so much stressed by the second wave of Corona. And with this nice talk with our Dean, and he has exempted all the PGs from COVID duties for ICU and wards. I think you are all now in a very happy mood, I think. It is the time to start our academic activities. And this type of class is nothing but it's a one-way discussion, one-way traffic. That I want to share. It should be a discussion part. And there should be exchange of ideas. That is why I started this lecture as an not as a monotonous one, and I want to share with our second year PGs. I'll have to answer with this Magill circuit. I already informed to you. Read about this Magill circuit and come for the class. Okay, we can go on to the class now proper. Magill circuit is very commonly used circuit nowadays. Now it is gradually the importance of the circuit is gradually coming down, and because of the high flow or the low flow systems are so much popularized nowadays, and use of the Magill circuit is very meager in our routine practice, and only for induction and then for recovery. Okay. Next. We can go to the slides. Magill circuit come under which classification? Whether Kanimuli is available? When Kanimuli?
Yes, sir.
We have to discuss with this. It is not. I'm not only the only one person talking with you. I would answer with this. Magill circuit come under which classification?
Semi-closed, sir.
Semi-closed. And come under which type of Mapleson classification?
Mapleson A, sir.
Mapleson A, yes. This 1954, Mapleson classified breathing system into 5 configurations. Is it? What are they? Mapleson A to E, A to E. And lastly, in 1972, I think, I don't know the exact year is, I don't know. And F was added to this letter. So, according to on what basis Mapleson classified these systems? At what basis? Hello? Hello? Kanimuli is there?
Sir. Sir, yes, sir.
On what basis Mapleson classified this system? Different? Any second year persons? On what basis?
So the position of the APL valves, sir.
Position of the, can you modify your answer in a very specific way? So Mapleson classification according to the efficiency of eliminating carbon dioxide during spontaneous respiration. Okay. According to the fresh gas flow. Start with this. System A requires, we'll go to the details. In a general idea, system A requires equal to the fresh gas flow equal to the minute ventilation. And when you take this Mapleson B and C system, that requires 1.5 to 2 times the patient minute ventilation. To averagely eliminate this carbon dioxide. And system D, E, and F, all are functionally similar, requires 2 to 3 times the patient minute ventilation to prevent CO2 accumulation or rebreathing during spontaneous ventilation. Okay. So on what basis it is, this question is very commonly asked in the examination. And according to the efficiency in elimination of carbon dioxide during spontaneous ventilation, Mapleson classified these circuits from A to E and the year 1975, I remember it. 1975, this F system is ordered. Okay. And what are the objectives of the breathing system? Or anybody is there or not? What is the objectives? What are the objectives to be fulfilled by this breathing system? It should deliver an oxygen, number one. And number two, it should remove the carbon dioxide from the patient. And number three, for delivery of inhaled anesthetic agents. What are the ideal breathing systems should contain? Any idea? Niveta is there or not? Hello? What are the properties of the ideal breathing system should have?
It should be simple and it should be safe, sir. It should permit spontaneous, manual, and controlled ventilation, sir. And it should not cause any barotrauma, sir. And it should easily remove the exhaled gases, sir.
So our idea is ideal breathing system should be very simple and safe, and it should require a minimum amount of fresh gas flow. So requiring low fresh gas flow, it should not waste our gases for anesthetic gases and oxygen, all those things. And very good, it could protect the barotrauma, and very simple to use and permits spontaneous manual control. It delivers the required amount of concentration to be delivered to the patient, and should be very compact and portable, lightweight, and it should have a very good elimination of carbon dioxide, and running cost should be very minimal and able to conserve the heat and moisture. Okay, thank you. What are the components of this Magill circuit? Components. What are all the components in the Magill circuit? Where is Niveta is there or not? It's not responding. What are the components? Yes, okay. Is watching or not? Yaar pesradare? Who is Kanimuli. What are the components here? Simple components.
Patient end, corrugated rubber tube, sir.
Patient end is the component. Patient end is the component of the breathing system. It should be answered like this. Patient end is one of the component. Yeah. How to say like this?
Sir, APL valve.
APL valve. Starting from this APL valve, come to one side. From the machine side or from the patient side?
From the machine side, tubings, sir.
Tubings, fresh gas flow.
Fresh gas flow, tubings.
Fresh gas flow attachment, number one. Number two is the
reservoir bag, sir.
Reservoir bag, and then?
And the tubings, sir.
Tubings.
Yes, sir.
Tubings, you can say like this. Corrugated breathing hose.
Oh, yes, sir.
Corrugated breathing hose. And then?
Then the APL valve, sir.
APL valve.
Then there will be the angle hose, sir.
Connectors. Angled connectors.
Yes, sir.
Very simple system. These are the components of the Mapleson A breathing system. So it is a fresh gas flow and reservoir bag, APL valve. That is APL. What is APL valve? APL, adjustable pressure limiting valve, and this connector to the patient end. This is for the machine end. This is for the patient end. Okay, very simple thing. And now come to this reservoir bag. What are the components in the reservoir bag? Anybody else? Usually,
It
this
has a-
reservoir bag is composed of rubber or plastic material, that is neoprene. And sometimes nowadays the latex-free bags are available. And the neck part should have 22 mm female connector in the neck, in the component. The neck part 22 mm female connector, and the tail end opposite from the neck, and the loop is provided. What for this loop in the reservoir bag? It facilitates, it holds the bag upside down, and which facilitates drying if the bag is reusable. Mostly we are using a bag which have reusable in manner, and this has the capacity is most important. What is the capacity of the reservoir bag? Is the standard adult is 2 liters, and for the pediatric 0.5 liter. So volume from 0.5 to 6 liters bags are available maximum. Okay. And what are the functions of the reservoir bag? There are 4 functions are there. The examiner commonly asks this question: what are the functions of the reservoir bag? Number 1 function is it acts as a reservoir. That means it allows gas to accumulate during exhalation. So that provides reservoir for gas for the next inspiration. So this permits rebreathing, allows more economical use of gases and prevent air dilution. So number 1 is to accumulation of gases during exhalation, number 1 point. And number 2 point, it provides a means whereby ventilation may be assisted or controlled. Okay. And number 3, it can serve through a visual or tactile observation as a monitor for patient on spontaneous ventilation. Number 3. And number 4, so the bag is the most distensible part of the circuit, and it protects the patient from excessive pressure during breathing system. Suppose there is any block in the circuit, whatever it may be, what happens to this block from anywhere else, from this machine end to the patient and up to the tracheobronchial tree, any block from this, the pressure will be mounted inside the circuit, and that was adjusted. Adjusted by this distension of this bag. It distends more than 4 times or 6 times. So these are all the functions of the reservoir bag. Number 1, first a reservoir. Number 2, it means whereby ventilation may be assisted or controlled. Number 3, it serves through a visual or tactile observation. And number 3, it protects from the excessive pressure in the breathing system. What are the ASTM standards for the reservoir bag? Anybody else? What are the ASTM standards? Anybody else? Does nobody know? ASTM means American, it is the agency, it's authorized in the world, that A for American standards of testing and materials. Without his permission, no machine or no devices will be coming to your market. Should get the permission from the ASTM. Reservoir bags of 1.5 liter or smaller the pressure shall be, it should withstand the pressure not less than 30 centimeter of water. And over 50 centimeter of water, the bag is expanded to its 4 times its capacity. That is the standard. For the bags less than 1.5 liter, the pressure shall be not less than 35 centimeter of water, or over 60 centimeter of water when the bag is expanded to 4 times its size. Okay, the ACM standards that decides the distensibility, how much the pressure that can accommodate to buffering the pressure inside the breathing circuit when it is in trouble. Okay, that is the ACM standards of reservoir bag. Next question. What are the various sizes available? I have already told earlier. That is 0.5 liter for the pediatric age group to up to 3 liters. Maximum up to 6 liters are available. And what is the problem in using this larger bag? Practical problem. Any practical problem? The larger the bag may be difficult to squeeze and make monitoring the patient and spontaneous ventilation is more difficult because as exertions of the tube, the bag will be very smaller. And what is the problem when using this smaller bag? Practical problem. The examiner will ask these simple practical questions. The smaller bag, on the other hand, provides less safety with respect to the pressure fluctuations and may not provide large enough reservoir or tidal volume. So, in the checking the machines, you should always look for it whether the spare bags are available or not. Any block in the system and distensible, and the bag will distend is 4 times higher, and there's a bag may tear about it, and it should be spare bag is available, but all the time. It is one of the most important pre-checklist. So spare bag should always be kept immediately available in case of any bag leaks or explosion. Okay. So these are all about the fundamentals regarding this reservoir bag. Okay. And regarding this breathing hose, when corrugated breathing hoses, what are the characteristics of the breathing hose? Anybody else? Very simple thing. What are the characteristics?
So the
breathing?
length of the tube should be minimum of 110
I am talking about, not talking about this Magill circuit proper in general.
Generally, it should be anaesthetic. It is a corrugated tube, sir.
Corrugated tube.
It should be to avoid kinking, sir.
To avoid kinking, okay.
And it should be made of antistatic material, sir.
To prevent static electricity.
Yes, sir.
So the characteristics should be, it should be flexible, number one. And number two, it should be low resistant. And number three, lightweight. These are all the standards, characteristics. So to have overcome this, to get these qualities, there should be an corrugation. Corrugation increases the flexibility, number one. And number two, it helps to prevent kinking. There are the two advantages in corrugation of these breathing tubes. One is increasing the flexibility of the tube. Number two, prevent kinking. These are the very simple things they asked in the examination. Okay. And what can you have knowledge about this tube holder? Tube holders are there nowadays. Now we are not using these tube holders because we are using nowadays using silicon tubes, which are all very lightweight, plastic tubes and reusable and disposable tubes. We are using this. In other days, In olden days, in our period, we are using this black tubes, black rubber tubes, which are all very heavy, and weight is very heavy and will drag our tube positions and will produce malposition of the tubing. Is a very common problem in those days. And that is why we are, in those days, your tube holders are most important, very commonly used. There are rounded openings are there in the adult breathing tubes, and opposite openings are for pediatric tubes. There are small holes in these tube holders, holes where it is tightly fit by this. And this device can be rotated according to the angles. Okay. And with this APL valve, what are the other names of the APL valve?
9 to 9:30, half-an-hour break.
Alone answer, you can mute yourself. Alone answer, you can mute yourself. What are all the other names for this APL valve? Adjustable pressure limiting valve.
Spill valve, sir.
Spill valve. Okay. Only one name. Yeah?
Pressure relief valve, pop-off valve.
Pressure relief valve, pop-off valve. Any other thing? There are roughly about 18 names are there for this pressure relief valve, APL valve. One is the pressure relief valve. Number 2, venting port. Number 3, relief valve. Number 4, overspill valve. Number 5, pop-off valve. Number 6, overflow valve. Number 7, dump valve. Number 8, blow-off valve. Number 9, safety relief valve. Number 9, excess valve. Number 10, heat brink valve. That is a very famous name. And number 11, adjustable pressure limiter. And number 12, excess gas venting valve. And number 13, spill valve. Number 14, exhaust valve. Number 15, expiratory valve. Number 16, excess gas valve. And number 17, pressure release valve. And number 18, release valve. These are all the names, other names of APL valve. At least you can say 2 or 3 in the examination. They will ask you what are the other names of this APL valve. And now we can go to this APL valve in proper. What are the components of this APL valve? What are all the components? What are all the components in APL valve? Anybody else? This APL valve has 3 ports. You can see this figure. One is the inlet and to the patient, and next to the exhaust. And the exhaust, that is exhaust here, that is open to this atmosphere. And this one is connected to this scavenging system. Okay. And there is a disc is there. Can able to appreciate the disc? Meanwhile, that is there. And the disc rests on the knife-edged seating. This is a seating here. There is a knife-edged seating here. Can able to appreciate this knife-edged seating. This disc is sitting over this knife-edged seating. And these are all the springs, loaded springs that will give constant pressure. To overcome this, opening this disc to push the disc to above, and this gas present in this circuit will produce such an amount of pressure to elevate the disc. That is the pressure offered by these spring-loaded rings. Okay. So the tension in the spring and therefore the valve's opening pressure are controlled by this valve dial. This valve dial is there, it is there. So what is the mechanism? The mechanism of action of this spring-loaded valve. There is a spring, otherwise called the disc and spring, or both are called spring-loaded disc. This one is the spring-loaded. The spring-loaded disc is there. This dark black is called disc, and these are all springs. So the most commonly used APL valve uses a disc held on the seat by a spring and with a threaded cap. This is a threaded cap. These threads are there. This is the threaded cap. Okay. These are all threaded cap. A threaded screw cap over the spring allows the pressure exerted by the spring on the disc to be varied. Suppose the cap is fully tightened. This cap is fully tightened. What happens? The disc will prevent any gas escaping from the system. And the cap is loosened. This cap is loosened. The gap will be maintained. The tension in the spring is reduced. Here it is highly tensed, fully closed, and it is open. The tension between the spring is reduced so that the disc can rise. Okay, can you able to understand this simple thing? When the pressure in the breathing system increases, it exerts an upward force on the disc naturally. This pressure in this breathing system increases, that exerts an upward force on the disc. When this upward force exceeds the downward force exerted by the spring, the disc rises and the gas flows through this valve. Okay, can you able to understand this? Suppose if the pressure in the system falls here, the disc returns to the seat like this when it is in a closed position. Okay, the disc come here and seated on the knife edge. When the cap is at maximum opening, there will be only minimal pressure exerted by the spring. This allows the patient exhalation to lift the disc only at the minimal pressure. Suppose the cap is fully open, the pressure needed for the disc to push up is very minimal. When the cap is fully opened, the weight and pressure on the disc ensures that the reservoir backfills before the disc rises. I will go into this in the functional analysis in later. So it is fully tightened. This cap is fully tightened. It needs extraordinary pressure is needed for the disc to open, to vent the gases. So that is why it is called, you can adjust the pressure according to our need. That is why this valve is called APL valve. That is adjustable pressure relief valve. Okay. And we can go to the general terminology. They will ask you in this rebreathing. What do you mean by rebreathing? Anybody else? What do you mean by rebreathing? without knowing this terminology, we can go in for this function analysis. We cannot able to understand it properly. Anybody else? What do you mean by rebreathing? That is the most important terminology used in anesthesia practice. It is very dangerous also. Okay.
Rebreathing of the exhaled air, sir.
Rebreathing, that is the correct terminology you are using. It means rebreathing means, please all can note it down. Rebreathing means to inhale previously respired gases, from which carbon dioxide may or may not have been removed. In the circle system, we are 100% rebreathing. Low flow system, 100% rebreathing. Here, the CO2 is completely removed. So, rebreathing means inhale the previously respired gases, previously expired gases or respired gases. That is the definition for rebreathing. Okay. And what are the factors? That is the rebreathing is the most important short notes as in the examination. And also they will talk much more regarding this in the afternoon session discussion regarding this rebreathing. If the circuit is given as a device for you for discussion. And what are the factors that will influence rebreathing? Number one, the most important one is first gas flow. That is the most important determining factor. The amount of rebreathing varies inversely with the total first gas flow. Less the flow, definitely rebreathing. More the flow, reducing rebreathing. So inverse relationship with the total first gas flow. Okay. Number two, the apparatus dead space that has the major influence. What do you mean by apparatus dead space? That is the another question is there. We'll discuss it. What do you mean by apparatus dead space? Anybody else? It's a very commonest question asked in the examination. And if you are giving any circuit to you, they will show you what is the apparatus dead space in this circuit. Can you show me? The examiner commonly asked. This question is very commonly asked in the examination, in the practical examination. For that, we have to understand what is apparatus dead space. Without knowing this, we cannot go into the functional analysis of this any circuit is concerned, because this is a very basic terminology that should be understood. Anybody else? What do you mean by apparatus dead space? Emily? Hello? Is there or not anybody else?
Yes, sir.
What do you mean by apparatus dead space? So,
Sir.
it is otherwise called a mechanical dead space. That is the volume in a breathing system. Please note it down. It is the volume in a breathing system occupied by gases that are all rebreathed without any change in composition. So up to what level in the apparatus, I mean the breathing system, the rebreathed gases are present. So in MAGILLS circuit A, and where this apparatus dead space is there, up to the APL valve, definitely the rebreathed gases are definitely they will be present. So any system with the expired valve is present up to this point, that is called apparatus dead space. So how will you minimize this apparatus dead space? Apparatus dead space can be minimized by separating the inspiratory and expiratory gas streams as close to the patient as possible. Okay. Now, what are the, we will come to the rebreathing. What are the factors that influencing rebreathing? About number one is called press gas flow, and number two is called apparatus dead space, and number three is called the breathing system design. There has a very major influence on this rebreathing. We will discuss it later. And there are the three factors. We can go into the details of this. We will discuss it later on during the subsequent class of the breathing systems. And next one is what are the effects of rebreathing? Very common physiological effect. CO2 mounting. That is very commonest answer they will expect from the examiners. CO2 level hypercopia is the very commonest effect of rebreathing, number one. And any other thing other than this, other than the CO2 accumulation, any other effects caused by rebreathing? Can you able to understand my question? Yeah, can you believe? Any other? Hello? Once the patient is rebreathed, what happens? There is a heat and there is a warm gas from this tachybronchial tree come there into the circuit, is it? So heat and moisture retention is very, very common. And number two, the patient is rebreathed. Apart from this hypercarbia, there is an altered inspired gas tension will be there. That is called the cushioning effect. Have you heard about this terminology, cushioning effect, by this rebreathing? So rebreathing alveolar gas exerts a cushioning effect on changes in the inspired gas concentration or composition. Am I correct? Because alveolar gas composition, we are again and again, we are breathing again and again. So what happens to this inhaled anesthetic concentration? The fresh gas flow anesthetic concentrations are not equal with the alveolar gas concentration, composition. Am I correct? So what happens during induction? So this induction, we are delivering low concentration of anesthetic gases and the induction is prolonged. The patient having rebreathing. So what happens during recovery? The physiology. The opposite will occur as like that of induction. There is a delayed recovery. So the alveolar gas tension exceeds the inspired gases and rebreathing slows the elimination of gases. So delayed recovery is the problem. So these are all the common facts, common fundamental physiological aspects of rebreathing. Okay. What is that is discussed. And the very common question asked in this examination, Magill circuit, who invented this and when? Anybody else? Who invented this and when? Breathing system, Mapleson. Mapleson, Magill circuit. Who invented this?
Sir, Ivan MAGILLS.
Sir Ivan Magill. And then, in which year? This question will be asked in the examination. And it is a very common short notes in the history of anesthesia. They will ask you this, Sir Ivan Magill. You have to write at least 10 points regarding this Ivan Magill. And 1920, he invented this. And what are the other inventions of this Magill? Yes, so much of contributions to anesthesia by Sir Ivan Magill. The Sir, that is the award, reward given by this King of Wales also. Any other inventions by Magill's? Magill's contribution to anesthesia. Anybody else? Rifan? Magill's blade.
Sir,
Magill's attachment. Magill's forceps.
Forceps, sir.
Magill circuit. Anything else? I think 4 or 5.
Yes, sir.
His contribution to MAGILL. Go and check it with it. Okay. Now we can describe the assembly. We have already assembled the assembly. We have described it. Press gas flow. Number 2 is a reservoir bag and corrugated hose, and then APL valve and the connectors for the patient end. This is the assembly of this Magill circuit. Very, very simple system. Very, very simple. The circuit is very simple without any complication as like that of closed circuit. Very simple system. Okay. And what is the functional analysis? Anybody else can describe it, or you have to describe. You have to describe this functional analysis. That the examiner will ask you the working principles of this Magill circuit. Anybody, can you say something regarding this working principle?
Sir,
What happens?
so during spontaneous ventilation, in inspiration, the gas will be inhaled from the reservoir bag, sir. That reservoir bag will be filled with fresh gas flow and the dead space gas, expired dead space gas, sir. During expiration, initial part of expiration, while the patient breathes, it comes from the dead space, so that enters the reservoir bag. And during the later part of expiration, when the pressure starts build up, the spill valve opens and the gas is expelled out, sir. So during the expiratory pass, while the fresh gas flow enters, and it fills the entire breathing system, sir. This is spontaneous ventilation.
Okay, good. But should be in a very clarity is not there. Okay, no problem. Here, during first inspiration, there is the first figure. During first inspiration, this reservoir bag and corrugated hose all filled by ideal fresh gas. Okay. And the ideal and attached and those system, the patient inspires, the gases are drawn into the lungs, and at the rate greater than the fresh gas flow, the rate of flow, that is the peak inspiratory flow, that is greater than the fresh gas flow. What happens to the reservoir bag? The reservoir bag partly empties. Am I correct? Can you able to understand this principle? During this first inspiration, this reservoir bag and hose are filled with this fresh gas flow, and this valve is open fully, and the patient is drawing gas from this hose, this fresh gas. If it is the peak inspiratory flow is actually 3 to 4 times the minute ventilation, and we cannot provide such a large amount of fresh gas flow. So this reservoir bag will act as a reservoir to contribute this peak inspiratory flow. That is why the fresh gas flow is not enough to handle the situation of the demand of the patient, and this reservoir bag give the contribution to this peak inspiratory flow, and its reservoir bag partially collapse, partially empties. Okay. And then next expiration, the point next figure, can follow me. The patient has to begin to exhale here because the reservoir bag is not full at the time. Reservoir bag is not full at the time. The exhaled gases are breathed back along the corrugated hose also, back towards the reservoir bag. Here, towards the reservoir bag. However, the exhaled gases can pass as far as the reservoir bag, and the latter can be the press gas flow is continuous flow. This can be filled during expiration, and part of the gas, the part of the corrugated hose will also fill by this, and this time the pressure mount in this system that will push the spring-loaded valve up, and some part of the gas starts to vented out. Okay. And during this expiratory pause, what happens? The fresh gas flow, almost this reservoir bag is almost filled, presumably, and push the gas. The first gas here is the dead space gas. That is, there is the gas not take part in the exchange, gaseous exchange. That is the gas present in the anatomical airway. It is occupied by this first part of this corrugated hose, and next part next to this are mixed alveolar gas. That is the gas take part in this alveolar gaseous exchange, and this fresh gas flow is maintained adequately with the minimal minute ventilation. This fresh gas flow will push all these mixed gas to the APL valve. What is here after this next start of this inspiration, this dead space gas will be there here, and followed by the fresh gas flow. So the flow is, the fresh gas flow is equal to our minute ventilation. The alveolar gases or the mixed alveolar gases are vented out, and the dead space gas and fresh gas flow is okay for the next inspiration. This is the working principle of this Magill circuit in spontaneous ventilation, provided the patient having spontaneous ventilation. So no problem at all. Almost the fresh gas flow is well maintained with a minute ventilation. Almost all the alveolar mixed gases are vented out. Okay. Any doubt, you can ask me later. And what happens this in controlled ventilation? The patient is controlled, paralyzed patient. When you are using this circuit, what happens? What happens during this controlled ventilation? Irfan? What happens during this controlled ventilation? Anybody else?
So during controlled ventilation,
Yes.
the expired gas will be
Expired gas will be
vented out, sir.
vented out fully. Vented out fully.
When we give positive pressure in the reservoir bag, sir, part of the gas will be vented out through the APL valve, sir, as it was distal to the reservoir bag. So it is not suitable for controlled ventilation, sir.
What is the working principle, man? What happens during inspiration? What happens during expiration? What happens during expiratory pass? Can you analyze this? So here I will come. I will discuss it later. I will explain it. You can follow me. During the inspiratory phase, see the figure. Inspiratory phase. The apial valve is kept closed or open. It should be closed, definitely. Apial valve is closed. But you have to squish the bag. There is no respiratory effort. It makes this controlled. You have to squish the bag to push the gases inside the lung. Is it? The bag is squished in first inspiration. The pressure mounted inside the circuit, which is more than the spring-loaded pressure disc. So it will open this valve somewhat, and some amount of the gas is expelled out through this valve, and major portion of this gas will be get inside the lungs during the respiration, first inspiration. So during inspiration, because of the pressure inside the circuit is mounted up to open the valve, and some amount of the inspired gas is vented out, and most of the inspired gas should be get inside the lung. Number one, can you able to understand this? And number two, during expiratory phase, at the end of inspiration, what happens to the reservoir bag? It is empty at the end of inspiration. The reservoir bag is empty because it is squeezed. So as soon as our anesthetist relaxes the pressure on it, the patient exhales through this tubing, corrugated rubber tubing. Am I correct? First come is the dead space gas, and next is the alveolar mixed gas. First come is the dead space gas. Right? So the exhaled and alveolar gas passes here because the pressure inside the circuit is low, because basically it's not attempting to exhale. The apial valve is not opened, and the pressure mounted here is low, and all the exhaled gases will go through this corrugated hose, and the part of it fills the reservoir bag also. Can you able to understand this point? So during controlled ventilation, almost all the corrugated rubber tube having this mixed alveolar gas and dead space gas and some amount of dead space gas and alveolar gas may filled by this reservoir bag also. So during this next act of inspiration, what is there here is the fresh gas flow, and we have to meet this peak inspiratory flow of this patient. And what are all there here in this gas, I mean this corrugated hose and this reservoir bag, it is a mixed gas and fresh gas flow, both are there. And all this, what is filled in this corrugated hose is both of dead space and mixed alveolar gas enter into this patient lung again. That is the problem when using this Magill circuit for controlled ventilation. So when the anesthetist squeezes the bag again, the first gas to enter in the patient lung will be the previously exhaled alveolar gases. The volume of gas that escaping via the apial valve during this second inspiratory phase is initially small, and during this phase, squeezing the bag, the pressure inside the system, the breathing system is gradually increased and high enough to open this valve, and part of the mixed alveolar gas and dead space gas are expelled out partly, and partly goes to the initially breathed is this alveolar gas followed by fresh gas flow. So in this system, we cannot able to eliminate this rebreathing when the patient is on controlled ventilation. Can you able to follow this? Please understand. Please understand. So in order to prevent this, what maybe we can do for it to prevent this rebreathing during controlled ventilation? The only thing what we have to do is to increase the fresh gas flow, to increase the pressure inside the breathing system, to open the valve, to exhale all the alveolar gases filled in the corrugated hose. Okay, am I correct? So how much amount of fresh gas flow is needed to completely wash out the alveolar gas present in the corrugated hose? Can you able to understand this? So it needs 3 times the patient minute ventilation. What is the minute ventilation of the adult patient? Anybody else? What is the minute ventilation of the patient?
70
Anybody?
ml
70 ml per kg.
per kg, sir.
So in a 60 kg man, we have to increase this 3 times. This is a 210 ml per kg. Our boils apparatus can able to meet out the demand by this patient. It is not possible, and rebreathing is inevitable in Magill's subgroup. Can you able to understand this physiology? If you able to understand this physiology today, I will be very happy. So that is why breathing Magill circuit is not opted for controlled ventilation. And if you increase this fresh gas flow to 2 to 3 times this normal, there is a highly wasteful with regard to fresh gas, and it will increase the potential for air pollution in the theatre. Almost all the theatre we are not using this scavenging system here, and the theatre is fully filled with alveolar gas. I mean, this inhaled our anesthetic gases, and we are all fed up with this. If we give this general anesthesia with controlled ventilation with using this circuit, almost all the persons inside this operation theatre will become fatigued and tired, and they will be very minimally anesthetized also. And definitely this Magill circuit is not suitable for controlled ventilation because inevitable. Rebreathing is inevitable. Okay, that is the basic physics behind this breathing Magill circuit as its working principle is concerned. Okay. Now, how do you check this circuit? How do you check this circuit? Pre-use check. Animally. How will you check this Magill circuit? Hello? Hello? Is there or not?
Yeah.
Animally, how will you check this Magill circuit? Have you used this circuit or not? Do you have any experience on it? Whether the Magill circuits are available in our theatre or not?
Only
Maples
one
and
available, sir.
only one thing is available. Okay, most of the persons are not exposed with this Mapleton A system. It is gradually obsolete now, but in those days we are all commonly using this Magill circuit that is only available circuit in our theater. Mapleton A system is tested for leaks by occluding the patient into the system, by closing the APL valve and pressurizing the system. And if you pressurize the system, the pressure inside the circuit is very high, mounted up, and it will raise the spring-loaded valve, and some amount of gas is exhaled or vented out through this APL valve. That denotes that the circuit is okay. Okay. This is the way we have to check the Magill circuit. Do you have any knowledge of this LAC system? What do you mean by this LAC system? Have you heard about this? The principle of this LAC system and Mapleton A system are same, but the physical arrangement of this Magill circuit and LAC system is somewhat different, but the working principle is same. If you answer all the questions regarding this Mapleton A circuit, the examiner will give this bonus mark. They will ask you about this LAC system. What are the types of LAC system? What are the problems of the Magill circuit that is overcome by the circuit? There are two Magill circuit that is known as the real. One, the valve, APL valve is very close to this patient. If you use this circuit for the head and neck surgery, if you use on spontaneous ventilation, and the APL valve near to the patient is very hindrance. So when you use this LAC system, it reduces the access to the valve in head and neck surgeries. And number two, the APL valve near the patient end will drag the mount and the connectors and lead on to what happens in malposition weathers. So increases the drag and the mass and the endotracheal tube, and the valve is now it is audible now. Audible now?
Yes, sir.
Audible. Okay. Now it is audible.
Yes, sir. Audible, sir.
Hello.
Audible, sir.
Okay. Thank you. And this lag system and the lag system has the coaxial circuits and parallel circuits also. What to say with this? There are two configurations are available in the lag system. One is the coaxial lag breathing system, and the other one is the lax parallel breathing system. And figure A, that is called the coaxial breathing system, and number B is called the parallel breathing system. What do you understand by this term coaxial? The examiner will ask you very frequently. If you ask all the questions regarding this Magill circuit is concerned, coaxial means tube inside the tube. Here, see the tube inside the tube. Here the APL valve is on the machine end, not the patient end. That is the modification. Here there are parallel tubes are available. Here the first gas flow goes through this outer tube to the patient, and the exhaled gases passes through this inner tube, and that is attached to the APL valve, and that is connected to the scavenging system that is vented out. That is the modification in Apparatus A circuit. That is by this lax coaxial system. There is tube inside the tube. And the other one is this lax parallel system. There are two tubes are there. One is for the inspiration and other one is for the expiration. And this expiratory tubing is connected to the APL wall and vented out. That is for the coaxial system. The coaxial breathing system has the working principles are the same as like that. There is no difference between this Apparatus A and coaxial breathing system, except this assembly is somewhat different. APL valve is very near to the machine end of the patient. And coaxial breathing system have the potential hazards also. The inner hose become disconnected to split as has been the leak may pass unnoticed here, and that will mount drastically alter the efficiency of the system in eliminating carbon dioxide. Therefore, it is very dangerous. This integrity of this inner tube, that is the exhale. The version of lax parallel system that will overcome this problem, and there are separate hosings for inspiration and expiration. So it is the next generation of this lax coaxial breathing system is an lax parallel breathing system. Okay. This is all about this lax system and Apparatus breathing circuit, Magill circuit. And these are all the scavenging system inside this original lax parallel system. It is a schematic diagram of lax coaxial breathing system. Coaxial means tube inside the tube. Here, what is the basic difference between Apparatus B and this lax system is the inner tube in main circuit, first gas flow will come down. Here the reverse will occur. This inner tube is meant for expiration and this outer tube is meant for inspiration. That is the difference between this Apparatus B and lax system. Okay. Lax parallel system. How will you test this inner tube in lax system? There is an extraordinary question. When you answer all the questions very smartly, they will ask like this. How will you test this? So this coaxial lag system requires additional testing to confirm the integrity of the inner tube. That is most important. One method is to attach the tracheal tube to the inner tubing at the pacing end of the system, blowing down the tube. Yeah, I will show you this. See like this. You can follow me. Okay. You can follow me. To attach the tracheal tube to the inner tubing at the pacing end of the system here. Okay, sorry. So blowing down the tube, this endotracheal tube with the apial valve closed will produce movements of the bag if there is a leak between these systems. So if there is any leak inside it, this inner tube is connected to the endotracheal tube, you have to blow off. If there is any leak here, this outer tube is connected to the reservoir bag and the leak will pass on to this and it will produce alterations in the reservoir bag, and there you can feel the movements of the reservoir bag. That is the test, very commonest simple test used to know the integrity of the inner tube in lax coaxial system. And another method is there. Here there is no problem at all. There are separate tubings are there, no problem at all here. This coaxial breathing, there is integrity is most important. Otherwise, CO2 accumulation will be there and it will produce a potential dangerous outcomes. And another method of testing this lag system is to occlude the both limbs at the patient connection with the apial valve open. You can occlude these both limbs here and apial valve open this apial valve, and you can have to squeeze the bag. If there is any leak in this inner tube, the gas will escape through this, come to this outer tube and get rid of the apial valve. Okay. So there are the two tests for testing the integrity of the inner tube in lag system. Okay. And I can come to the end, carry home message. Mapilson breathing system that is effective for spontaneous ventilation, and the plus gas flow required is the minute ventilation, that is about 70 ml per kg per minute. And it is not for controlled ventilation. It needs 3 times a minute ventilation is needed. And Mapilson A, the apial valve is the patient end. And it is not suitable for pediatric practice also, because the apparatus dead space volume is very high, and that is why it is not suitable for pediatric population. And regarding this reservoir bag is concerned, made up of rubber and plastic, and various sizes are available, and there are functions of the reservoir bag is most important, and the most important function is the reservoir. It acts as a reservoir. It accommodates the flush gas flow. It will meet out the demand for this peak inspirative flow by the patient, and it can assist and control ventilation. It is a monitoring system for whether the tidal exchange is adequate or not, and it is a buffer for the pressure inside the circuit. It limit the pressure build up in the breathing system. And apial valve, there is 3 things are available. That is a spring adjusts the pressure required to open the valve. When fully opened, the pressure needed is less than 1 centimeter of water. And it is a safety mechanism. It is actuated at 6 centimeter of water when it is closed. And regarding this lag breathing system, it is a next generation of Mapilson A. It is a coaxial version, tube inside the tube, making it efficient for spontaneous ventilation. And the first gas flow needed is like just like that of our mepilation A, that is 70 ml per kg. And here the first gas flow is delivered along the outside tube and exhaled gases follow flow along the inner tube, and APL valve here is in the machinian, not in the Pacinian, and it is also definitely not suitable for control ventilation. Okay, thank you so much. Thank you so much for the nice patience. And any questions,